So there we go, there's our path for the storm. If we have a front, well, cold front, we tend to have precipitation in front of and at the front. Behind the front, clearer, cooler, less humid. Warm front, we tend to have more mild precipitation associated with the front. Afterwards, clearer and warmer and more humid. Stationary, different sides, things can be, are you on the cold side or the warm side? You'll have different conditions. On the warm side, typically it's going to be relatively humid and rainy due to the front being nearby. Also, a front can tend to kind of steer a low pressure system. If that comes along next to our stationary front, then you can have heavy rain with it. Temperature variations. We have the variations associated with Earth's rotation on its axis. Again, as the Earth spins, day and night. Yep, it's warmer in the day and cooler at night most of the time. Revolution around the sun. We've got our seasons as the Earth goes around in its orbit. We mentioned before, we've got a complication. Clouds during the daytime block the sunshine, make it cooler. At the night, they help trap heat being lost from the Earth, make it warmer. So cloudier, well, is the nighttime or daytime effect bigger? Depends on your exact pattern of clouds. There we go, seasons with the Earth's revolution, the orbit. Wind. If the wind's coming from someplace where the temperature is different from here, it'll tend to change your temperature. Is it blowing from someplace warm, blowing from someplace cooler? That's advection. A common pattern, if things are calm at night, right towards the ground is the area that, of course, gets warmed most by the ground. So that's going to cool off the most as we move into the night. And we can get a temperature inversion with cooler air down there and somewhat warmer air higher up. Now, if we've got winds mixing things around, bring some of that warm air down, cooler air up. Don't have winds, we won't see that. Snow and ice. Of course, very high albedo, so that tends to cool things down. Less is being absorbed, more is reflected. When they do melt, then we have to be putting in latent heat. So as they melt, they're keeping the temperature cool. It's not until things have largely melted that we can warm up again. Precipitation. Well, do we have air cooling off, such as it's rising? And how much moisture is in the air? I'll check on the dew points. Is the dew point very low compared to actual temperature? Then we probably won't get precipitation. It probably won't cool down that much. If the dew point is close to the actual temperature, but a little lower, won't be hard to cool down to that and start making clouds and maybe either dew or frost or precipitation. What type? Is it going to be rainy? Is it going to be snowy? This drift conveniently blocked my sidewalk in New York, not here. What's our temperature pattern in the air? Okay, that's a lot of information. How do we put that all into one forecast? Probably we need a computer there. And then we can analyze the data. And so computer forecasting is also referred to as numerical weather forecasting, NWP. To get a very good forecast, it takes a very complex model, and so supercomputers are used. Even so, this is not going to be completely perfect. The models do have simplifications, limitations, and so different models will give somewhat different results. And so part of the work of being a weatherman is to take these different models and try to figure out, okay, how much do they agree, where they don't agree, what are you going to actually tell people as the expectation there. Also, even if our model were perfect, it needs the right data. We do not have a complete coverage of weather information, and that's something that can potentially be worked on. There was a study a couple years back where they deployed an extensive set of weather meters right in our part of the world, and indeed had better forecasting ability than what could be done just with the existing standard weather measuring out there. Now, whether government's going to actually budget to invest long term in better coverage, well, we'll see. But at any rate, more data can help, and where we don't have as good data, we don't have as good weather coverage there. Another challenge is that the math going into these models turns out to be chaotic. In the technical mathematical sense, what this means is that you've got this nice formula, looks relatively simple, but it turns out that the answer you get out of it can be very different in response to only a tiny difference in the numbers that you put in. This was discovered for weather forecasting because somebody had a computer going along making weather forecasts, and then something went wrong. They had to restart things, and so they went back a bit and put in the number that was being used at that point. And when they restarted, wait a moment, this is not the same results that we had just a moment ago from this same computer doing the same calculations. Turned out the number that they entered to restart the simulation was routed off a little bit from the number actually being used by the computer, and that tiny difference was enough to cause major differences in the prediction as you got further out in time. This is sometimes described as the butterfly effect, the idea that a butterfly flaps its wings here, and that over long term is enough difference that it could be that now there's a hurricane somewhere that wouldn't have happened without the butterfly, or maybe that stops the hurricane. Yes, our weather formulas, it turns out that basically to be able to predict what the weather is going to be, say, a month from now, precisely, we would pretty much need to know what all the atoms in the air are doing. We don't know that. And so, as we get longer term, there's going to be more and more uncertainties and errors in our prediction.